Thank you for watching our presentation on reinforcement learning with vision-based state estimation for generalized robotic assembly. My name is Mark Trovinger, and I am a PhD student at Mississippi State University in the Department of Computer Science and Engineering. For our project, we looked at robotic construction, and going along with that is reinforcement learning and vision-based state estimation. In order to validate our approaches, we used simulation and lab experimentation using a Canova arm for the lab and a Franca Panda arm for the simulator. In the simulator, we used our wooden blocks to assemble simple structures. When we discuss the use of reinforcement learning, we need to look at low-level control, which is the primary method for using manipulators, and we ran into some scalability issues as task complexity increased, and so we needed to use a different approach. We'll discuss that in a little bit. So for robotic construction especially, there have been existing works that have looked at possible approaches to this problem, both from assembly tasks such as bricklaying or concrete printing, but also planning methods as well. So in the case of doing crane lift planning, how do you build a structure in a way that allows for proper pieces to be placed where they're supposed to go? In terms of learning methods for robotic construction, that has been done for timber joints along with doing it from demonstration. So a model is shown how to do a task, and then it is hopefully able to repeat that task. So for our state-based estimation, because this is a combination of vision-based state estimation along with reinforcement learning, we used OpenCV's fine contours to detect the objects in the frame, and then we used a two-dimensional on the x and y axis prediction to generate data points, which were then used to move the arm to where it needed to go. And you can see here in the image that we have our wooden block detection pipeline, and our coordinate system is at the top left corner of the image is the origin, and the location for these blocks is extracted, and how much movement needs to be done is based on that. We can see here that we have an R squared score of 0.9865 for X and 0.9985 for Y. Now, one of the limitations, and this will be discussed a little bit more at the end, but this vision-based system is working currently under the assumption that in order to pick up the blocks, first off, they have to be rectangular and wooden, and also that they are a certain distance from the camera. Obviously, we would like that to become more generalized as based on the name of our paper. And so in the future, instead of using this method, we would use a CNN-based method in order to achieve this goal. Now, we also did some pre-processing in order to make computation a little bit faster, but thankfully this does not affect overall performance. So for reinforcement learning, we worked on initially using low-level control and then looked at using deterministic actions. So in the case of low-level control, we found that as the task complexity increased beyond a simple pick and place, the algorithms had a very hard time trying to actually solve that, and the success rate, even for a simple pick and place, was very low. Deterministic actions, on the other hand, where the action is essentially pre-programmed, we found to work much better. And so using a small subset of possible actions as deterministic, meaning the algorithm doesn't need to learn every single movement, we were able to use Q-learning, and instead of making it a planning problem, to turn it into a traveling salesman problem. So we use these very selected actions in order to solve this as a shortest path problem. And so the optimal policy then will solve in the minimum number of steps with also the highest success rate. And so in order to do that, we needed a reward function, and our reward function is essentially minimizing the number of steps taken for object assembly. Now, what that means is essentially that we know that it's going to take so many steps in order to use all of these actions in the correct order, and so the fewer number of times it would need to repeat an action, the more closer to the optimal policy it would get. for the reinforcement learning methodology, we define the state space as the number of wooden blocks that remain within the scene. And so our action space is defined as moving to a block, opening or closing the gripper, or moving to the objective position, meaning which block corresponds to which objective. And so in order to have these objects moved in the shortest possible time, the reward function is simply defined as the negative sum of the time steps taken for each task. So a longer number of time steps will indicate that the object is not being moved in the most efficient way possible. These are our results for using the simulator and using our RL proposed method. So we can see here that the tower assembly has a greater success rate along with the wall than traditional RL approaches, and success rate was the primary metric by which we judged how well this method worked. If the deterministic method is able to solve in a much more repeatable fashion, that demonstrates that it is a better approach than using traditional low-level control for RL. We can see here in the image from the simulator that the simulator is able to build the objects, and it shows the objects being built sort of in real time. So for our lab testbed, we looked at several different tower assemblies, and we'll have more detailed images of these in a little bit. But the physical tests indicate that the robot is able to build it. Now, the difference between the simulator environment and the lab environment is that the simulator runs at 25 hertz, and certain actions are assumed to be essentially instantaneous, such as opening and closing the gripper. And so it is not exactly an apples-to-apples comparison for time. So the simulator is able to complete the tower in very, very short time periods, whereas the real robot obviously takes substantially longer. And so one of the other methods for optimization, or the same method, would be to a pickup order, so making sure that blocks are placed in the correct order. And that is when we move from using the RL method to simulator to using it in the real world would be something we want to work on. As this result image loads here, we will see that this is using one of the algorithms, the low-level control algorithm, and we can see that the position of the arm is not close to where it should be. It is way over off in the side here. This is indicative of some of the issues that were mentioned with this particular approach. The algorithm tries a lot of random motion before it learns more accurately what motions lead to the best result. And so we can see here there's a lot of wasted motion, and so the algorithm is not really able to converge to an optimal solution. Whereas using a deterministic policy, or deterministic actions, I should say, we are able to build both the tower and the wall, and we are able to achieve the goals of able to create these objects with a very high success rate and repeatable. These are more images of the tower or the wall, being built in the lab, and you can see here as the tower or the wall progresses how it is able to build it in the correct manner. This is similar to the tower here. We can see, although these images are slightly out of order, we can see that it is able to turn the blocks the correct way, and so we are able to accurately pick up and then place the blocks. Some observations and discussions. As mentioned earlier, we are assuming that the z distance between our end effector and our target is fixed. That won't always obviously be the case. And we are only rotating in the z-axis in order to place the blocks in the correct orientation. And we are only really using the vision input for initial stages. And while this could scale up to larger construction environments, it relies upon accurate simulators, and building accurate simulators is a very difficult process and would require a lot of work on its own. So our references used for this presentation, and I want to thank you for watching.